Okay, so I think we're good on time. It's 9:30, so let's get started. There's a bunch of things I want to cover today, including maybe some time towards the end about an outlook of what we've done so far and what else you could think about. Okay, so welcome to the last class. We've been working our way towards analyzing the generalized Lotka-Volterra model in the high dimensional limit this entire class. And so today what we're going to do is we're going to go outside of this fixed point assumption, fixed point regime that we were working in the past 2 or 3 classes. And in particular, we're going to go to this unstable phase that we derived yesterday. That's once your sigma becomes high enough, higher than some sigma critical, you generically go into a phase in which you don't see fixed point dynamics anymore. And we're going to show today and basically talk today about what kinds of arguments that we can make about what the dynamics look like in a quantitative way, rather than just saying, oh, it's chaotic and there's crazy fluctuations, right? So we're going to make sense of what all are the statements that we can say about the dynamics in this regime. And the method by which we're going to do that is called dynamical mean field theory. It's again a generalization that you might have seen in other statistical physics systems. And the central idea is to again go from a system with a large number of interacting variables to one effective dynamical equation describing any one particle, right? And so in this case, it would be any one species. And again, we're going to exploit the fact that all the species are statistically identical. We're going to see that, of course, in this case, we won't look at fixed points. So that's why the dynamical, right? We'll actually look at things changing with time. And so it'll help us to see, using some results from simulations and also some arguments that we'll make, that actually the right way to analyze these dynamics is by rescaling the abundances and by rescaling the time by essentially a new quantity that we'll introduce, which is some sort of small migration rate. So what we'll do is we'll take these generalized Lotka-Volterra equations, which by now I hope you have committed to heart. We're going to work in a situation where we add a small migration rate lambda for all species. And then, of course, then we'll care about doing everything in the limit where lambda goes to 0 from the plus side, right? You're kind of, this lambda is kind of telling you every species is coming in from somewhere outside. Maybe there's some mainland from which species are migrating, and all of them are migrating at some small rate lambda. And of course, thus far, what we've been looking at is essentially a case where lambda equals 0. So today we'll introduce this small lambda and anyway go to the limit where lambda goes to 0 from the plus side. Okay, we'll see that that will be very useful in both regularizing the dynamics and helping us think about this whole rescaling process, because this lambda is going to be a very important quantity that's going to show up kind of again and again and again today. And that's indeed going to be the basis for this rescaling. And we'll see that once we have this right lambda, these are really the right key variables that lead to the collapse of the correlators for this kind of DMFT. Okay, and once we get a rescaled version of this DMFT, I'll keep saying DMFT in this class, by that I mean dynamical mean field theory. The rescaled version of this DMFT in the rescaled abundances and rescaled time, we'll see as a very nice interpretation as a stochastic process between two impenetrable walls. Okay, and we'll see where those two walls come from. Essentially, one of the walls will come from a migration floor, that is, species don't quite go extinct. Every time they're just about to go extinct, some migration can bring a small amount of them back. That's one wall. And the other wall will be a self-organized wall set by the interaction of all the species together that will, in the end, limit the growth of the species and prevent them from blowing up. Okay. And then finally, what we'll see as a result of kind of analyzing this effective stochastic process between two impenetrable walls, we'll see that we can make arguments for what the dynamics should look like. And we'll see that the dynamics will look like this, of this boom and bust type. That is, what you'll often see is that there'll be lots of species, there'll be some very, very rare species at some very, very low abundance, and you'll suddenly see them jumping up to sort of order 1 abundances. That's kind of like a boom. And as species are going and booming from this very low abundance to this very high, or to this sort of order 1 abundance, we'll see that that also causes the slow march of some high abundance order 1 species, which get knocked down by these booms, and they sort of slowly march towards rarity. So there's this constant churn over in this community where some species are rare, they suddenly boom up, and that causes, and that will somehow then cause other species to start going down, and this continuous churn over basically goes on forever, and that's sort of how chaotic dynamics are manifest in this system. Yeah, and sort of all of the stuff that we're going to talk about today has been analyzed and discussed in this very nice PRX from last year. So if you are interested in more things that we won't talk about, we won't talk about everything from this paper. If you're interested in more stuff, you can take a look at this paper. Yeah. All right. So let's sort of begin. So like I said, thus far we've been studying properties of the fixed points of these GLV dynamics with lambda equals 0. Right. So that's setting this thing 0 for all species. Today we won't do this. Today instead we'll stick to analyzing the full sort of dynamics. And also we will analyze these dynamics in the limit where we are in the unstable or multiple attractor regime. So just to remind you, kind of yesterday, we had derived this sort of stability criterion, which, at least in some simple cases, was that this critical sigma was something like 1 over rho, it was root 2 over 1 plus rho. Right? So that is, if sigma, to remind you, sigma characterizes the standard deviation of the interactions Aij, that becomes larger than this value that's set by some rho that we choose, then we'll go, if sigma goes over this value, we'll go unstable. And so that's really the regime that we will be working in. And of course, we argued that things become unstable, so you shouldn't necessarily see things sitting at a fixed point, but it's always, of course, nice to ask ourselves then what the dynamics look like, right? So if you actually simulate these dynamics, what you'll see is the following. So I'll first just kind of draw, just to set our brains into what we should be expecting to see. I'll first draw a case for sigma less than sigma critical. Right, that's everything is fine. You're in the unique fixed point phase. And in this case, if we have our abundances over here, and remember what we said in the first class, we're always going to plot this in the log scale. So, this can be some 10 to the minus 1, this can be some 10 to the minus 4, this can be some 10 to the minus 7, and so on and so forth. You'll start off with some abundances. Some species will go up and rise in abundance and settle down. Some species will, of course, march on to extinction and die away. And if we have this little lambda over here, let's say that lambda is very, very small. Let's say that's something like 10 to the minus 10 or something like that. Then instead of going extinct at long time, all of these extinct species will kind of go and settle at this small value over here, right? And this is kind of going to be what we're going to call the migration flow, right? But for all intents and purposes, these species are what we've been calling the surviving species. There's some number S star. And this species is essentially like the extinct species. That is, in the absence of lambda, they would actually go extinct. Right? This is what was happening in the unique fixed point phase. There is no what dependence? There, like we derived yesterday in the phase diagram, the mu doesn't really matter. If, as long as you're not in this infeasible region, the critical sigma is independent of mu. It's a flat line. So now let's ask ourselves what happens when sigma goes over sigma critical. So you can, again, there's no problem with doing these simulations. Nothing terrible happens. What you'll see instead is the following. every species, so to remind you, every trajectory I'm drawing here is one species, will start to exhibit this kind of persistent fluctuations. Okay? And there will be persistent fluctuations essentially that seem to be limited on the top and at the bottom in these two ways. So at the bottom, as you might expect, they're still kind of getting close to this migration floor. Remind us is kind of set by lambda, right? That's what we are going to call, for all intents and purposes in the rest of today's class, low abundance, right? In physics, whenever we say low, it's low with respect to something. So whenever species abundances are of order lambda or so. And then there's another thing over here, which is roughly like some order 1 abundance. That these species don't seem to be going over, and roughly order 1 abundance is what we're going to call high abundance, right? And really what you kind of see is that species, like every trajectory of every species, kind of flits back and forth between this high abundance and low and sort of low abundance, right? You kind of see these fluctuations that go on and on and on and on. Lambda definitely has a role to play, but we'll see exactly what this picture is. Maybe I'll hold off that question for later in the class, because that's exactly how do we think about what's going on is exactly the sort of point of today's lecture. Yeah? Okay, and so is this clear what you'll see? So this is kind of our basis for trying to see whether or not there are chaotic dynamics or not. Okay, and just to remind you, or not to remind you, but to tell you, there's a small little addendum that this is actually only true as long as rho is not equal to 1. Okay, I'll tell you maybe towards the end of this class that when rho equals 1, you actually do not ever get chaos. In that special case, actually, you can formulate these dynamics in terms of a Lyapunov function. You can write down a Hamiltonian for them. And actually, then in that case, when you break stability, instead of going to a chaotic phase, you go to a phase with from one globally stable fixed point phase to a phase where there are multiple stable fixed points, right? So that you have multiple wells. So I'll talk about that maybe towards the end. But in the rest of this class, we're going to be concerned with rho not being 1. And in fact, actually, for simplicity, what I'll show you later is that actually we'll stick without any loss of generality to the case where rho equals 0. So just to remind you what this rho was a correlation between the diagonally opposite entries of this matrix, right, Aij and Aji. So when rho equals 0, that just means that every entry in this matrix is IID, right? Aij and Aji don't talk to each other. Okay. This is just for mathematical convenience, and you'll see exactly why this mathematical convenience arises. Okay, so the key thing that I want you to take away from this is that kind of there's already this idea that we had in the first class that because there's this exponential growth process, it kind of makes sense for us to think about the abundances in log space, right? There's every time if you were to say draw a histogram of what happens at the end to species abundances, that histogram would have 2 peaks on the log scale, right? There'd be a peak here and there'd be a peak here. This peak would correspond to this Gaussian-ish part that we had sort of derived yesterday, right? And this peak would be everything that would otherwise was sitting at n equals 0, right? These were all extinct species that will not be extinct anymore. So we're already sort of gearing up to thinking about logs of the abundances as being somewhat the natural thing for us to think about. These dynamics are happening in log space. Okay? All right. So now the main question is that that's fine. Things are happening in log space, but how do we start to describe these dynamics, right? Remember, like what we did yesterday with the what we did over the past 2 classes with the cavity method, we always restricted ourselves to ni dot equal to 0. That's not going to be a good description of things in this phase, right? So we're going to have to explicitly account for the time dependence of everything. And so for that, what we're going to do is we are going to derive the dynamical mean field theory for this model. Now, there are many ways to derive this dynamical mean field theory. So if some of you have already encountered generating function formalisms, Martin-Ségier rows, and so on, you can get the equation that we're going to get using those formalisms. We have to pick one to do in this class. And so what we're going to use today is something called the dynamical cavity method. Okay, which is just, as you can imagine from the name, it's a dynamical version of the cavity method. Okay, and what I mean by that is, thus far in the cavity method, we were always assuming that you start off from a steady state, you add a cavity species, you go to a new steady state. And I said to you before that we're going to relax this assumption. We are going to relax that assumption now. Okay, so what we're going to assume now is that where you have a system with S species which are following some trajectory. You introduce a cavity species to it, and you go from an old set of trajectory, from an old trajectory to a new trajectory. Yeah? So the cavity species essentially modifies the trajectory that the system was on before, as opposed to modifying the fixed point. Right? It's a small change, but that's really what will make all of the difference. Okay? And can you say that a little bit louder? Is it like adding cavity and, sorry, what? Traveling to all other, what do you mean traveling to all other trajectories? So what I mean is the following. I mean, there are two ways to think about a trajectory, right? You can think about the trajectory in phase space. Any system will have one trajectory, right? That's some high dimensional trajectory. Or you could think about the trajectory of any individual species. For our purposes, they're both going to be the same thing, right? I mean, like if you perturb the trajectory of the entire system in phase space, that's essentially like you can break it up into components where each dimension is a species, and you'll perturb the trajectory of every species. If you're confused about this, it'll all become clear in a minute, so we don't have to fluff about it, yeah? Okay, so just like in the cavity method, in the end, we derived some equation for n0 at the fixed point, right? This time, our goal is not going to be to come up with the fixed point abundance of this cavity species. Our goal is going to be to come up with an effective dynamical equation for one randomly chosen species. For any one randomly chosen species. And just like what we had before, we're always going to invoke arguments of the type where all species are statistically identical. So if you can derive a self-consistent effective dynamical equation for any one randomly chosen degree of freedom, the statistics of that essentially describe the effective dynamics of every degree of freedom. Right? That's just the idea that we're going to use. Okay, at this time we're not going to focus on the fixed point behavior. Okay, so the idea is again very simple. So we'll just kind of go through all of the steps that we go through with the cavity method, but just with this dynamical wrinkle to it. And you'll also get to maybe brush up what we did in the cavity method in this sort of process. Yeah, so what we're going to do is we're going to introduce a cavity species. That's going to have some abundances n0, which is now time dependent, right? So I'm going to keep writing for a while this time dependence again and again to remind us that things are now all time dependent. Eventually, I'm going to stop writing it because it's going to get annoying. But for now, I'll write it down. Yeah. And what we're going to ask is how the trajectory of the system is perturbed. Okay, and to see this, let's do the following. Let's just write down the dynamics of any species I that was in the system before we introduced the cavity species. That's just going to be, to remind you, it's just going to be Ni dot of t is Ni of t times some Ki minus Ni of t minus sum of Aij and j of t minus what will happen if I introduce this cavity species? You get another inhibition from this cavity species, right? But now this is Ai0 and 0 of t. Right? It's literally the same equation here. I'm just explicitly writing down the time dependence of everything. And I'm just reminding myself that the parameters are not time dependent. Right? Later, once we do everything in this class, we'll see that we can make those things time dependent as well. And we can be fine. Okay, but for now, the parameters are still fixed, quenched. Our degrees of freedom are now time dependent. And all we've done is we're looking at the perturbed trajectory of species I in the presence of the cavity species, right? And so what did we do at this point? Oh, well, I forgot, but I'll always keep writing my lambda. Okay, so what did we argue when we were doing the cavity method? What's the effect of the cavity species on the trajectory of every other species? So it doesn't affect much, but it affects something somewhat, right? So what did we argue at this point? Exactly, that we argued that you can think about the cavity species inhibition as essentially a change to the carrying capacity, right? You go from a situation where your Ki, which was fixed, goes to Ki of t, right? Which is basically your old Ki plus some delta Ki of t, right? So you had some Ki to sort of begin with. You now have a time-dependent perturbation to the carrying capacity, right? I'll just keep saying the word time-dependent again and again and again in this class, just to remind ourselves that that's the key change that we have, right? So as soon as you have, even if you had a fixed carrying capacity, you now have a time-varying carrying capacity, right? Because you have a time-dependent perturbation. And we argued last time that this perturbation was going to be small, right? Because this AI0 was order 1 over S, right? Of course, this N0 of t is usually limited from the top by some order 1 high sort of abundance. So if this is 1 over S, then this can be at most order 1. This whole thing is going to be small, order 1 over S, while this is order 1. Right? So it's a small time-dependent perturbation. And what did that allow us to do last time? Yeah, use linear response, right? Okay, so let's just write down what we, and what's the key quantity that we introduced when we were writing down linear response? The susceptibility, right? But what we had last time was just one matrix, right? That was what is called a static susceptibility, right? It was asking if I change the carrying capacity of species J by a little bit, how much do I change the steady state abundance of species I, right? That's mu ij. Now, of course, everything is time dependent. So what we need is a 2-time susceptibility matrix. That's what we'll introduce. And I'll describe what I mean by 2-time. That 2-time susceptibility, something I'm going to write down as mu jk But now, again, like everything else, it depends on t and t prime. Why should it depend on t and t prime? Why should it depend on 2 times now? Right. And what does that mean physically? Yeah, I mean, it's the sort of standard thing that we write down, right? You make a perturbation at time t prime, and you ask for the effect of the perturbation or the response at time t, right? That's the idea, right? So what this is del n j of t over del k of t prime, right? You make a perturbation to the carrying capacity of species K at time t prime. You ask for the effect or the change in the abundance of species J at time t. Makes sense? Let's just get a sense of what this means. What can we say from causality? It must be true about this new JK prime. Can we say something about what happens for t less than t prime? It should be 0, right? Why should it be 0? You're making a you're making a perturbation after you look at the time, you look at the response, right? So that of course should be 0, right? That's just causality. And so of course what we're looking at are situations where t is greater than t prime, right? Okay, and so now let's write down what we get from linear response. What we get should be an equation for the trajectory of species J, that's nj of t. And that we write approximately, because this is linear response approximation, as nj without 0 of t. What is this guy? This is the trajectory that species J was following before you introduced this cavity species, right? So of t reminds me that it's a trajectory minus, now again I have this sum over k, but what do I do? Earlier I used to write a susceptibility and then the change in k, right? What do I need to do now instead? Because I have a 2 times susceptibility. I still sum over all species that are perturbed, but now I have to integrate over time, right? So I have an integral now that goes over t prime of nu jk t prime, and my perturbation is ak0 and 0 without t, with a minus sign, right? So that's where my minus sign is coming from. Okay, we're all good. This is just linear response, right? Oh, sorry, is there a mistake in what I've written? This should be t prime, right? I apply the perturbation of the cavity species at t prime. I ask for the response at t, right? So this whole thing should not depend on t prime, right? So this is my, just to remind you, this is my perturbation. This is my response. Right? And I'm just integrating over all time, all species. Okay? It just looks a little bit more involved. It's exactly the same thing that we did two classes ago, right? Okay, so now then what did we do? We now know the perturbed trajectories of every species, but we don't know the perturbed trajectory of the cavity species, right? So we can also write down that. We can write down a cavity self-consistency equation. Which is the effect of every species on the cavity species. So now I want to write down the dynamics of the cavity species. So I'd write n0 of t dot, right? That's n0 of t, k0 of k0 minus n0 of t minus A0j nj of t plus lambda. That's all, of course, fine. The main thing I need to do is to substitute this nj of t using this linear response approximation. Okay. And if I do this, simple substitution, so I'll just do it here, but all the crux of the things I'll write over there. That's going to give me k0 minus n0 of t minus a0j nj without 0 of t plus, now it's a double sum over jk with an integral mu jk dt prime a0j ak0 n0 of t prime plus lambda. Okay, really simple. We just substituted. I just wrote down this thing when now summed over j gives me now double sum with an integral. I've just put in the a0j inside. It's a constant. Is everyone okay with that? Okay, and what did we do last time then at this point in the static cavity method? Yeah, we solved for n0 at fixed point, right? So what we cared about was, oh, now we care about n0 at fixed point, so it can either be 0 or when this whole thing is negative, or it can be 0 when this whole thing is 0. Now we don't have that, right? Now we don't care about fixed points. The system we know is not going to a fixed point. So we'll have to deal with this entire equation, right? With an n0t dot on this side, right? What we are looking for is essentially an equation that only involves n0, right? Where we can say something in terms just n0. If we end up with a single particle equation, then maybe we can analyze something about it, right? And you can kind of try, and you can kind of start to see that the kind of equation that we'll end up with is going to be effectively a stochastic equation. Why is that? What was our argument for what this guy was when this was not time dependent in the static cavity method? This was going to be some random variable, right? What we're going to assume now, again, this is an ansatz, it may be false, but again, we'll verify it later self-consistently. What we're going to assume now is that this thing is for similar reasons as what we had last time. Not, of course, a Gaussian random field, but like a Gaussian process, right? Everyone's okay with what a Gaussian process is? Did they do Gaussian processes in the prep part? Okay, it's a stochastic process that's well defined by its first two moments, right? So what we're just going to care about is we're going to assume that this is a Gaussian process, and what that's going to make, what's that going to result in is that it's going to make the effective k, which is this guy over here, a Gaussian process, right? And we then also have to worry about this terrible guy over here, right? So what can we do with this sort of terrible guy? Well, we'll do the following. But I'm going to argue in a second that what we'll do to it will tell us is actually very, very hard to deal with this entire guy because it makes the entire stochastic equation non-Markovian. Okay? This guy is essentially a memory kernel. Why is it a memory kernel? You're carrying forth information from what happened to the system before at all times, right? So really, I mean, we could do what we did last time in the static cavity method, try to analyze it, assume that this sum also involves a Gaussian process, care about its moments. You'll end up getting something of this type again, you'll end up getting something like sigma square rho over S, sum over J, integral dt prime, nu jj dt prime, n0 of t prime. If you do sort of all the standard things that we did before in the cavity method. Again, if you're confused about this, I'll leave it to you as homework. Exactly the same arguments as what we applied before, except there's just an integral in time hanging around. This guy over here, you can inspect, right? This is kind of an average with the sum of many, many species. We can again assume this self-averaging-ish idea where what's happening to the jth species is also happening to every other species. So we could replace this guy with essentially what's happening to the 0th species. But you still kind of see that whatever this is, which we don't know, remember last time also we ended up with something that was like the trace, the average trace of the susceptibility, right? That's kind of what the analog of this is. But this is now still a kind of a matrix, right? Because, or still a kind of a two-time operator. And this is still a memory kernel that makes this whole equation non-Markovian, right? So just somehow if this was not there, then we would be fine. We would have a stochastic process where the sum part is a Gaussian process, something is just our degree of freedom, and then there's just a constant lambda, right? That thing we could hope to do something with. Okay, so it would be amazing if we didn't have to deal with this memory kernel, at least in some limit, so that we can do further analysis, and then we could later ask how much of a difference this memory kernel makes. Yeah, so can you see something about what I've written over here that would indeed make it so that you wouldn't have to worry about this term at all? What delta? You're saying that you can assume something about this memory kernel. I'm not talking about assuming something about this memory kernel. I'm talking about killing this term. Rho equals 0, right? So if rho equals 0, this whole term goes away, right? No matter what happens to this complicated memory kernel, there's at least one case for which we don't have to worry about this entire thing, right? Rho equal to 0, memory term goes away. And what we will see is that in this situation, we can actually really analyze what the dynamics do and look like. And then we can ask ourselves everything that we learn about what the phenomenology is, how robust is that for cases where rho is not 0, and of course also not 1, remember? So all of these other infinitude of cases you can inspect numerically, and that paper will show you and try to convince you that the phenomenology is not affected by the presence of this memory term. Okay, so that's what we're going to deal with for the rest of this class. So let's just write down finally what's the equation that we ended up with. We have n0 dot of t is n0 of t times sum k0 minus a0j n0 of t, oh sorry, not n0 of t, nj without 0 of t minus n0 of t plus lambda. That looks more handleable. And we already argued that we're going to think about this as a Gaussian process. And we're just going to call it some g of t, some little g of t. Okay, this entire term we're going to call some g of t, or g0 of t if you want. Okay, so we're now here on our last step for our DMFT, and then we'll be done. Thus far, everything that we've been writing down is for the cavity species, right? What's the last step that we did in the cavity method? The cavity species is just statistically identical to every other species, right? So we can just drop this 0. And that gives us our final equation, which we're going to spend the rest of the class analyzing. So we get n dot of t is n of t times g of t minus n of t plus lambda. This g of t is some Gaussian process. So we also want to think about the statistics of this guy. Of course, this equation is not well defined without that. So what's the mean of g of t? Is it k, or does this have 0 mean? No, right? This is going to give us a mean, which is the mean of k. And that's going to give us what? The mean of this guy times the mean of this guy, right? The mean of A0j was what? Mu over S. And then this and really you can see that this whole thing is nothing but now a time-dependent average abundance, right? So if you want, you can call it something like M of t, right? So you can also write this down as k minus mu mean n of t, where again the mean of n of t is a process that we don't know, right? We again have to self-consistently find it, just like we did in the static version. And we also need to define the correlator of g. G of t prime. That also is something that we can derive. And in fact, I'll write down g of t prime minus this guy over here. And that we're going to see is going to be sigma square times n of t prime. Okay, same arguments as sort of before. You know what g of t is. So you can compute what g of t prime is. This is just simple substitution. You'll see that you will end up with a term which involves nj without 0 at t and nj without 0 at t prime. Nj is n0 is n, right, because of self-averaging. And so that's just going to give us this correlator over here, n of t prime, the expectation of n of t prime. Right? This is also something that we don't know, but we need to self-consistently find. Right? So we have analogs of lots of quantities that we got in the static method popping up here as well that we don't know and need to determine self-consistently, right? There's the mean. This is the analog of the variance or the second moment, right? There was a susceptibility which we threw away, right? And then there was some notion of phi, right, which is the fraction of things that go extinct, which now we don't need to worry about for a second because of that lambda, right? Nothing will really go extinct. We might still care about how many species are at the migration floor at very low abundance, but we will see sort of how to talk about that. Okay? And that kind of completes at least the description of this stochastic process, right? We now have a self-consistent equation for a single particle or a single species, along with these two self-consistency relations. And if we can kind of solve this DMFT, then we're done, right? Just like what we were arguing for last time. If you could solve the means and the second moments of the n's and the phi's and the nus, then we were done. Okay. So now what's kind of left, and what I want that I want to spend maybe the next 20 to 30 minutes talking about, is how do we make sense of all of this algebra, right? What is it telling us qualitatively about the dynamics? Because remember, we've said nothing about that so far, right? We've only just applied the cavity method full steam ahead to it, right? We ended up with a DMFT equation, but physics only happens when we then analyze what the equation is trying to tell us, right? So let's do that. Okay, so what we really need to proceed now is really an ansatz, right? Just like we had an ansatz last time, that there's a truncated Gaussian, so we can write down some set of self-consistency equations using this truncated Gaussian ansatz. We need to come up with an ansatz, and the key thing that we need to come up with an ansatz for is really the correlator, right? We need this mean of n of t prime. Okay, so here again, we turn to numerics to ask ourselves, what does a correlator actually look like if you actually simulate this equation? Okay, that's indeed what you would do, right? You, rather than walking around the lawn like 50 times and trying to guess what it should be, you should just ask what it is. Okay, so if you kind of plot, what we're going to plot is this quantity, mean of n of t prime. I'm just going to call that C of t comma t prime, right? Everyone's okay with how you would numerically estimate this quantity? How would you do it? You'll generate a trajectory of n, meaning for like from these equations, right? By numerically evolving them. Okay, you have these trajectories, then like ni of t, right? For some chosen species I, yeah. Yeah, you'll average over these for many species at different times t that you start off from, right? So just to sort of repeat, you'll pick sort of one of these species simulated using the full high dimensional dynamics. You'll start off from some t for that species, then you have, you know ni of t, and you'll just proceed at any t prime after that and just literally compute this product, and then you'll average over all of your species, and then you look at that for different times, right? So when you plot that, this is what you see. So this is now the x-axis is going to be the time difference. That's t minus t prime, or rather t prime, what do I do? T minus t prime. Okay, and what I'm going to plot here is C of t comma t prime. We're also going to start calling this guy tau. T, if again, if you've seen this before, then you're familiar why. And so this can also be thought of as C of tau. This is our correlator. And if you plot it, you'll see that it looks something like this. Okay, and you can do that starting from some time t, maybe some early time. You can do it for some later time. You can do it for some other later time. And really, they'll really be on top of each other. I've just kind of displaced them for like visual purposes. But yeah, you'll kind of see that after you wait for some initial transient period, if you sort of start after that, this correlator would look this way. And just to kind of tell you, this is all happening at a fixed value of lambda. Right? So that might be, let's say, lambda of 10 to the minus 10, as we were discussing. Okay, so what does that tell us? Does that tell us some nice property of C of t comma t prime? Exactly, it's time translationally invariant, right? You can think of C of t comma t prime, which could have been as complicated a function as you might imagine, but it actually just depends on t minus t prime. Right? That's kind of why we've actually written it down as C of tau. So that's kind of nice. That's really nice. That makes things simpler. There's another thing that you can do. This is actually important and a key observation in this paper, which is that you can make this same plot that we just made here. So tau goes on the x-axis, C of tau goes on the y-axis. And you can do it for different values of lambda. Okay, remember we eventually want to think about the lambda going to 0 limit, right? So if you do it for different values of lambda, here is what you'll find. So for some value of lambda, it'll look like this. Some other value of lambda, it'll look like this. Some other value of lambda, it'll look like this. And really, do you think as you go from orange to green, you're increasing lambda or decreasing lambda? Anyone have any intuition? Do you understand what we are plotting here? This is some lambda 1, this is some lambda 2, this is some lambda 3. That is, you do the same exercise as what we've done here. This was for one value of lambda. You got one curve basically. You can do it now for another value of lambda. Same procedure. You'll get that curve. And another value of lambda, this is actually the direction of decreasing lambda. Bringing in more species, we're not bringing in more species, right? This is the rate at which species are coming in. This is like every time, like every species is being brought in at the exact same rate, right? That is lambda. That's why it's not lambda sub I. Exactly, right? Yeah. So you can imagine like why this should be this case, right? But the key observation in this paper is the following. If you have different values of lambda and you look at C of tau at tau, there's no collapse of the correlation function, right? It of course depends on lambda. But you can do the following rescaling of time. You can now work instead in a rescaled time, which is basically tau over mod of log lambda. Okay, you can again plot C of tau over log lambda. That actually gives you a collapse. So in this rescaled time, all of these three different colors go on top of each other. And what that's telling us is that this is really a nice unit in which to look at time. Okay? And just to sort of give you a sense, this log lambda is really in some sense the time it takes for a species to kind of start off from the migration floor and go up all the way to some order 1 abundance. Why is that? Can someone argue why that would be? Okay, what should be the time it takes a species to sojourn from the migration floor, which is where it has an abundance of roughly lambda, to order 1? It's growing exponentially at some rate k, right, which is roughly order 1, right? So if you're growing exponentially from lambda to 1, how much time should that take you? Roughly mod of log lambda, right? If you're not okay with that argument, think about it for 10 seconds. You still can't come up with it, come to me after class, right? So this really has a nice interpretation. It's a slow time scale of the problem that really has an interpretation of the time it takes to go from floor to top, to go from rare to abundant. Okay, so that really motivates us to think about some rescaled version of time. Okay, and so similarly, it also motivates us, this whole thing that we were talking about at the beginning of the class, to similarly look at a rescaled abundance as well. That's also something that we will do. It will be useful to work in, instead of n's, to work in what we'll call z's, where z of I is log ni over, again, this mean of log lambda. And again, another way to kind of think about this, this is kind of the minimum abundance that a species would have. You're just kind of scaling, this is just like the log ratio of the current abundance to the minimum abundance, right? This is that kind of rescaling. So we'll work in units now. Instead of n's, we'll work in z's. And again, we're not talking about species I anymore, right? We're talking about any focal species that we care about. And instead of time as t, we'll talk about this rescaled time, which we'll call s, which is again rescaled by this mod of log lambda. Okay, and now all I'm going to do is a very simple algebra where we're just going to do a change of variables of this DMFT to variables z and s instead of n and t. Okay, and that's going to allow us to write down a rescaled version of this DMFT. Okay, so I'm going to leave it to you as homework to do that change of variables. I mean, I already told you what the change of variables is, to do algebraic substitution. Huh? You have to be smart. But basically, I think that was like one of the big kind of achievements of this paper, which is the way that they found the rescaling factor is, again, observing the fact that if you do this rescaling, you get this collapse, right? And like I said, like one way you could argue that you might think of that is that that is a relevant time scale of this problem, right? You see in this problem again and again sojourns from rare to abundant, and you can ask how long that takes typically, and then that gives you a time scale, right? So you can ask what happens, and you can I mean, some hint that you get that lambda is of course important, right? If you change lambda, you change what this correlator looks like, right? So clearly it suggests to you that you should do some sort of scaling with lambda to get some sort of collapse, right? Linearized equation in this case will not help you. No, actually, in this case, actually, that doesn't help. What actually helps is actually taking this n over on this side, recognizing that this is just log ni dot, right? And so that actually helps you see that this will become lambda over ni, right? So you kind of start to see that actually all of the relevant time scales in this problem and the length scales, meaning the abundance scales in this problem, have to do with comparison with lambda. Yeah. Okay, I really want to move ahead, but yeah, I mean, this is a good question of how you guess these things, right? This is really, I mean, a lot of this stuff is you make a nice guess, you have a nice ansatz, and you see if it works or not, right? If it doesn't work, then you move on and you try something else, right? Okay, so after you sort of rescale, I mean, yeah, what you end up getting is the following. Yeah, I won't go through the algebraic steps. Now, instead of an equation for dn dt, we'll end up getting an equation for what? N will become z, t will become s, so we'll get an equation for dz ds, right? Which I'll just write down as z prime of s. That will be g of t will become g of s plus these two other terms. Okay, this is some straightforward algebraic manipulation, but so I leave that to you. And the only thing that you need to do is you take your n of t to this side, you sort of divide both sides by n of t. You'll end up with log of n of t dot here. And you remember that log of n is nice because that's what will give us a z. And you end up with just g of t minus n of t here. right? So G of t just becomes a G of s, right? And then basically there are two terms that are left over. There's an n of t, and then there's a lambda over n. And basically, I think this one is the lambda over n, this one is the n of t. Okay, so there were just, we should have an accounting of where all the terms went, right? This became z prime of s, this became g of s, this became that term, that became that term. Okay, again, how it became, if it looks mysterious, just sit down for 30 seconds and you'll be able to do, it's just algebra. Okay, but this equation is actually very nice, okay, because imagine taking the lambda going to 0 plus limit, because that's what we're interested in, right? What do you think happens to this term in the lambda going to 0 plus limit? Let's look at some nice limits of these two terms over here. This g is a little bit boring for now. So while I'm writing this, why don't all of you try to think and work out what the relevant limits of this thing are. So I'll tell you, for this guy, something happens when z is minus 1, z is less than minus 1, greater than minus 1, or less than minus 1. Right? And you can see that minus 1 is, of course, the relevant thing to worry about here. So, what's this limit when z is greater than minus 1? It goes to 0, right? Again, you guys are better at finding limits than I am. What about z is less than minus 1? Sorry? It blows up, right? Is this actually a case where a blow up is nice? Okay? Before I talk about what this blow up means, let's just also look at the other exponential term in the limit lambda going to 0. So this is e to the mod log lambda z of s. And again, here the relevant thing would be whether z is less than 0 or greater than 0. So what are the limits when z is less than 0? It goes to 0. And when z is greater than 0, blows up, right? So what is this telling us? Look, this is a stochastic process, right? Why is this a stochastic process? That guy is a stochastic Gaussian process, right? This is a stochastic process, and this z is going all over the place, right? But this z is actually confined. And it's confined between minus 1 and 0, right? If z goes above 0, you get this huge suppression, you're brought down. If z goes below minus 1, you get this huge push up. That's a plus sign, you get pulled up, right? So essentially, this is a stochastic process with two impenetrable walls, two hard walls. This is the kind of picture. This is z of s, that's 0, that's minus 1, and z is doing whatever it's doing stochastically between minus 1 and 0, outside of, when it tries to go above 0, it gets a strong push towards the left, that decreases it, and when it goes below minus 1, gets a strong push up, right? And this is actually has a very, both these pushes have a clear interpretation of where they're coming from, right? This thing over here is a push down. This is coming from some sort of emergent self-limitation. This is all the other species which determine g of s start to push you, right? This is when you hit some time varying carrying capacity, right? When you hit a time varying carrying capacity, you can't grow anymore, right? This is not your own carrying capacity. Remember, this is K minus sum of A0, J, and J without zero, right? This is all the other species are creating an environment for you that is inhibiting your growth, right? So this is an emergent self-inhibition or self-limitation that comes essentially from logistic growth, right? You can imagine that process was G of t minus N of t times N of t, right? That part is just logistic growth, right? But it's some logistic growth with a time varying carrying capacity, right? So the time varying carrying capacity is what pushes you to the left. And this thing over here, this is at some very low abundance, right? Remember, Z of minus 1 is a situation where your abundance is really, really tiny. And so this push is because of migration, right? So this kind of explains this picture that we had anyway, right? You're sort of confined, your sort of dynamics are confined between these two walls, one wall at high abundance, one wall at low abundance. And that's exactly what this DMFT is telling us, right? And the rescaled DMFT is kind of telling us it much clearer than the non-rescaled DMFT. So another way that I can write down this same stochastic process, now that we recognize that these are essentially walls, are in terms of these wall functions. I can write down some wall functions, W, where the wall function W of Z is 0 if Z is greater than 0, and sorry, infinity if Z is greater than 0, 0 if Z is less than 0. That's another way for me to write down my rescaled DMF. Right? And in this rescaled version, we can see everything that's going on. There are two walls. If I'm at the walls, I get pushed. If I'm not at the walls, it's like I don't feel anything, right? And in that case, what's my process? It's just Z changes according to G of S, right? Which is again some Gaussian process, right? So it's like essentially I have two walls between which I have a Brownian walk, right? I have some Z of t does some Brownian motion, is rough, etc., etc. As soon as I hit one of these walls, I get pushed rapidly to the left. I continue my Brownian motion, and then again, as soon as I hit this wall, I get pushed rapidly, and so on and so forth. So I'm doing like a stochastic random walk between these two impenetrable walls. It goes on forever. Right? This is kind of one way for us to think about our chaotic dynamics. This is happening for one species, but of course, this one species is every species. So every species is essentially doing this. Okay? All right, there's one more nice thing that we can now try and see. There's a lot of, like a lot more juice that we can extract from this stochastic process now that we see that it's this walk between two walls. Okay, so to do that, I'll just erase this bit. Okay, we have time. We will indeed do exactly that. Right, so now that we recognize it's a walk with these boundaries, we can actually impose boundary conditions and ask what we get. Right? Just to kind of complete this description, remember I kind of wrote things down in terms of Z of S. I should have also written down my statistics of G in terms of S, right? So I can just have my, like for instance, my correlator G of S prime minus, maybe if I want to write it this way, G of S prime will become sigma square C of S minus S prime, where C is now my correlator in this rescale time. And you can similarly write down the mean. Okay, but now I kind of want to analyze the following things. So remember, we argued that that stochastic process is telling us, let's just try and ask what happens to this walk, to this stochastic process near this Z equals 0. Okay, so imagine that we are right now below z equals 0, and then we're going to go close to z equals 0. Okay, so for z equals 0, everything is simple, right? What do we get? We get essentially, we want to write down n. Remember, we care about the abundances, right? So n of s, you can write down kind of straightforwardly as just e of log lambda z of s, at least in the lambda going to 0 plus limit. That there's no ambiguity. Let's now try to look at z going to 0. So if z going to 0, lambda going to 0 plus, at this dual sort of limit, in this case, things are ambiguous, right? So I need to use my boundary conditions. We can impose these now a nice boundary condition at z equals 0. And what's our boundary condition at z equals 0? It's an impenetrable wall, right? So can there be any flux through this wall? Yeah, it's a no flux boundary condition at z equals 0, right? So what does that mean? Z prime of s is 0 at z equals 0, right? That's my impenetrability condition. When z equals 0. And so in this case, what do I get? G of s is w of z, right? Z prime of s is 0. I'm far away from this -1 wall, so that gives me 0, right? So that means gs minus w of z is 0. That means g of s is w of z, right? These equations are simple. What does that mean? We can immediately now write down again the quantity that we care about, which is n, at this rescale time. N of s is just, that means g of s, but I just put this theta function with the convention theta of 0 is 1, just to remind myself that this only happens when z equals 0. Right? What is this telling us? That my abundances, n of s, right? S, remember, is just rescale time, right? So my abundances in this rescale time, at least when z equals 0, are just like this random Gaussian Brownian walk, right? Outside of that, there's something else, right? What are they? Well, if z is going to be less than 0, it's just going to be some sort of exponential decline, right? So really there's quite a simple picture that we get, that basically this is essentially just like saying that in the limit of lambda going to 0 plus, if your high abundance, by high abundance I mean order 1 abundance, that's a situation in which z is roughly 0, right? Log of n, log of 1 is 0. So that's the situation that we're talking about. Remember, z equals 0 is like n is roughly order 1. Then in that case, basically, you're at an approximate steady state. Right? That's exactly what this impenetrability condition is telling us. Right? Why is it an approximate steady state? Well, of course, it's not a true steady state because n is time dependent. This g of s, remember, is some rough Brownian walk, right? But it's approximately steady state because the Z is not changing with S, right? The rescaled abundance is not changing with rescaled time. Okay, so you're at some sort of pseudo steady state of sorts. Right? So when you get to high sort of abundance, what this equation is telling us, that any species that kind of gets to high abundance and the limit of lambda going to 0 plus, it's kind of like it kind of hovers there for a while and kind of just does some random Brownian motion, right? That's why it's not a fixed point, right? It's not a true fixed point because then n would really reach a fixed value, right? But it's kind of doing an effective stochastic process, right? Kind of a rough walk. And outside of that, it's just kind of doing smooth sojourns down or smooth sojourns up. Okay? So now this kind of really helps us write down some nice self-consistency equations that we can solve exactly numerically. And again, I won't have time to talk about how you solve these equations sort of numerically, but you end up basically now with this three set of equations. You have z prime s is g of s plus w of minus z minus 1 minus w of z. That's our rescaled DMFT. And then we also have basically our mean of g of s is 1 minus mu times, again, mean of n of s, right? But n of s, we argued, was basically g of s whenever z is 0. And again, g of s prime minus mean of g of s prime is sigma squared mean of g of s prime, and these two theta functions. Okay, these three equations, do they depend on lambda at all? There's no lambda dependence anymore, right? They have a well-defined lambda going to 0 plus limit. So in this case, you can solve them exactly numerically. Again, the procedure of that I'll leave you. I'll sort of leave for now. But if you're interested, come to me later. I just want to spend 5 minutes just talking about what's the picture again that we kind of get out of this. And there are two pictures I want to draw. One is again this effective low dimensional picture in terms of this z and n. And then one is the high dimensional picture of what we think is actually going on in the full high dimensional dynamics. That was one of the questions that was asked earlier. Okay, so what does this stochastic process look like? So the way to see what this stochastic process looks like is actually to make this fun graph. So what we'll draw here on the x-axis is s, that to remind you is rescaled time. And on the y-axis, we'll do something that's a little bit funny, but it'll make sense in a bit. And if you haven't understood all this jiggery-pokery that we've done in the last 5 minutes, hopefully you will now. So I'll draw this y-axis actually in two colors. Okay, there's going to be this 0 point. And over here, when things are below 0, here I'm going to plot z of s, which to remind you is log of n over mean of mod of log lambda. Okay, so I'm going to plot z whenever z is below 0. And I'm going to plot actually n whenever z hits 0. Okay, that's the argument that we made here, right? There's one regime in which z is less than 0, one regime in which z is equal to 0, and those two have slightly different behaviors in terms of what is going on. So what's sort of happening here is that your z of, you can focus on one species, and maybe this species starts off in a situation where it's not order 1 abundance, some intermediate abundance. You start to track Z. Z is doing something, it's some process, right? It does something, 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 it suddenly hits Z equals 0. Okay? At that point, what happens? You reach this approximate steady state, right? This guy goes from a small abundance and it makes a shoot. It jumps up suddenly to some decent abundance, and at this point starts to do some rough Brownian motion. So there's two things that I want to talk about. So not Brownian itself, but Brownian-like, right? In the sense that it's a rough walk. This G of S is not smooth. G of S is rough. G of S has this funny bit over here, right? This G of S itself has a sum of these many random processes. What you can show and what I'm not going to show is that if you actually look at this correlator and you look at C prime at 0 plus, that's actually finite. So then this is really just like a rough process. Yeah, but that was in tau, right? I didn't show it to you in rescale time. In rescale time, it looks very different. Yeah, exactly. Right? So really, because what you're doing in this rescaling, and this is actually good that you brought it up because this is what I want to talk about, right? You're taking time and you're rescaling it by log of lambda, right? And we want to go to the lambda going to 0 plus limit. That denominator is going to be a gigantic number, right? So really, what you're going to do in this correlator is you're going to squeeze the hell out of it to the left, right? So whatever looks smooth to you will look very sharp to you. So that's exactly how it will be like a delta function. And so in rescale time, things actually do look very rough, right? In real time, things will look smooth, as we've seen, right? But it's really this rescale time that kind of matters, right? So in this rescale time, you have this G of S, which is like a Brownian walk, and that's why it's kind of rough. And outside of that, things are not G of S anymore, right? Things are like that, right? So that even in rescale time, it's kind of like a slow relaxation and so on and so forth, right? So there's this kind of rough area, and there's this kind of smooth area. And so really what can happen is that it does something, it hits and goes below below the Z equals 0 again, and then at that point, you start to do something kind of smooth again. Maybe you come back up, and then again, sort of relevant to look at what's happening here. You can have a jump, and maybe later on, just go back down, settle to the migration floor for a while. Okay? This thing over here, I'm calling a jump. Right? And that's why I made this sort of dashed line over here, because it's a discontinuous process. The claim here is that as soon as this Z hits 0 and sort of crosses over, in terms of N, what is happening is that you have a species which is at some intermediate low sort of abundance. It goes up smoothly and hits something that's sort of order 1 abundance. All of that happens in finite time. Well, Zs cannot cross 0. That's what we just spent our time arguing, right? This is not Zs anymore, right? This is kind of two plots squeezed into one to kind of show us things happening along one trajectory, right? So Z equals 0, remember, is a hard wall. Z can't go above it. Above that, I just made a different plot that's just kind of emphasizing that at this point, it's not useful to look at Z. It's just useful to look at N, right? And so my claim is, like, what this discontinuity just represents is the finite time it takes for a species to go from some low abundance to some high abundance. It takes finite time in T, but it takes no time in S, right? And that's why it's like a jump. It's a discontinuous jump, right? So there's one stochastic process, there's a discontinuous jump process, and then there's another rough stochastic process, right? So this is the kind of effective picture of the dynamics that we end up getting, right? There's a smooth walk in between these wells. There's a very sudden jump, and then there's this rough walk, right? So really kind of what's happening is that there are species that at some low sort of abundance, they're smoothly hanging around there for a while. At some point, they cross the z equal to 0 barrier. They hit the z equal to 0 barrier, and they start to bloom. They start to go up in abundance. And as they go up, up, up in abundance, and this is the part that I haven't proved because I don't have the time, it's not like species keep accumulating up at the top at sort of high abundance. At some point, new species coming from the bottom are going to cause some species from the top to start going down. And essentially, that's kind of, one way of thinking about this is that eventually, whenever this high abundance species is sort of goes close to this small or relatively less than order 1 abundance, it's very susceptible to new species coming up and knocking them down. Because as soon as they make their z go down below 0, then they're just going to sojourn down. Right? So there are these boom and bust dynamics for all the species that you kind of see. Species go from rare to common, cause other species to go from common to rare, and this process, this continual churnover goes on and on and on and on. Right? This was just a random picture that we were talking about. That's just a description of what we see in these dynamics. This is a more quantitative way for us to see exactly what kind of stochastic processes are at play. Right? And so this is really one low-dimensional picture of the chaotic dynamics in this phase. Okay? So the final thing that I want to say is that really the high-dimensional version of this picture is just the following. Remember, where you're in this bit over here, z equals 0, right? And what we argued over here is that you're approximately, species are at some approximate steady state, right? In the sort of high-dimensional version of the dynamics, this is essentially like saying that the entire set of species that are at high sort of abundance, that are order 1 abundance, are near some fixed point of the dynamics. They're not at the fixed point of the dynamics, but they're near it. And they're near, this again you can show, I'm not showing today. You can show that this fixed point is stable, and it would have been stable were it not for those dastardly kids hanging around at the bottom of this migration floor. So all of these species are near some stable fixed point, but it's susceptible to invasion from species that are rare. And so what we think is really going on is that you can imagine some abstract high-dimensional phase space where there are all these fixed points, maybe these 2 to the s fixed points that we've been talking about, that are all unstable to invasion by species that would otherwise go extinct in the absence of sort of immigration. And what your high-dimensional trajectory is probably doing is that it spends some time in the vicinity of one of these fixed points. That's like this orange bit. It suddenly gets shot down and moves over. Right? Some other species come up, some other species go down. It goes down and starts to sojourn around some other fixed point. It goes to sojourn around some other fixed point after zooming in, and some other, and some other, and some other, and some other. So it's really like a pinball machine a little bit, right? You have this high-dimensional pinball where your trajectories are going close to some fixed points that are unstable to invasion, getting knocked out, getting close to some other fixed point, and this keeps going on and on and on and on, right? So another description of this chaos would be that you can kind of think about this as a Markov process or a Markov chain that's sojourning between these different fixed points, right? And then one way to maybe describe the sort of ergodic behavior of this would then be to describe the stationary distribution of this effective Markov process. Yeah, so that's kind of one way in which we think, or one can think about these chaotic dynamics. Okay, of course, as usual, I took much longer than I thought I would. So I won't talk about this rho equal to 1 business where you don't see chaos. What I will just say is that, rho equals 1, sorry, that when rho equals 1, things are much simpler because you can write this, you can write down an exact Hamiltonian for these equations. You can also add noise to these dynamics at this point, like actual demographic noise. And you can still write that down in terms of Hamiltonian. And then all you need to care about is to write down and extremize some free energy. And in this case, to do that, you use something called the replica trick, which I hope you will learn in the next week. So hopefully when you come back and you've learned your replica trick, you can try and either come to me or look up what the Hamiltonian for the system is when rho equals 1. Apply the replica trick to that, and you can sort of work out what the dynamics of the system would be, at least when these AIJs are symmetric matrices in the presence of noise, in the presence of immigration, et cetera, et cetera. Okay, I think that gives a more or less broad picture of at least GLV dynamics that we've looked at over at least the last 4 days, if not the last 5 days. To remind you, we kind of started off with the idea of what doing ecology was, looking at population dynamics, thinking about all these patches and their heterogeneity, focusing on one patch. We talked about consumer resource models and how they reduced to Lotka-Volterra models in the limit where resource dynamics are fast. We then spent all our time studying the properties of these GLV dynamics, first when there were 2 species, and then where there were a large number of species. We then looked at how do we think about the fixed point behaviors, feasibility, stability, and today we finally talked about what happens when you sort of breaks stability, right? There's lots of other things that you can do. You can go beyond these GLV dynamics. For instance, a lot of the work that we do in my group involves studying what happens to consumer resource models, not just of the type of the sort of MacArthur type I talked in class 1, but then generalizations of that involve things like cross-feeding, where species can eat resources and produce others, that involve multiple trophic layers, where you don't just have species and resources, you also have carnivores or predators of those species, and then predators of those, and then predators of those. You can also go and look at how you describe the dynamics or the properties of the multiple attractor phase, in particular this phase where there are multiple stable states. One of the things that you can ask yourself is, are all of the stable states equally likely, or are some states more likely than others? You can ask a similar question here in this kind of Markov chain, by the way. Are some things going to be more likely to be visited, some others less likely to be visited? And that's like describing a high-dimensional landscape of attractors, right? So many other things that one can do. Of course, I'm not going to be able to do justice to all the different questions that one can ask. But really, I think the final point that I want to make is that a common thing in theoretical ecology is not just to explain the data that we see from ecosystems extremely carefully quantitatively, but to also study these kinds of conceptual models, the kind that we've been studying, to look at qualitative behavior, right? And it's really surprising, at least it was to me, that studying models that look as simple as this can actually reveal extremely rich phenomenology and behavior. Right? And I hope I've sort of convinced you that that's the case. The simplest models that you can write down that you would not even deign to think that they would be worth your time can actually reveal a lot of really interesting phenomenology that actually has bearing on what we see out in the world around us. Yeah, so it really informs how we think about the kinds of dynamics that we see out there. Okay, and so with that, thanks a lot for being in the room the past 5 days. You can reach out to me If you have any more questions, I'll be around. I'm on campus, but this is my email address. You can also find it on the ICTS website. Yeah, please feel free to write to me. Okay? All right, thanks.